So this video is on the properties of logarithms, and this would apply to logarithms of any base, so base n, base e, it doesn't matter. So the log base b of m times n is equal to the log of m base b plus log n base b. The log of m over n is simply log m minus log n. And if we have log base b, m raised to the power of b, what happens is that p is going to move to the front, and we would simply have p times log m base b. So, and if log m is equal to log n for any base b, then it implies m has to be equal to n. So if you look at the first example here, we have log base 3 9 times x, and if we use the product rule, we could split it up and write it as a sum. Log 9 plus log x, the base is 3. So here we have 4 over 5 and the base is 1 over 4. And using the rule, we could split it up and write it as log 4 minus log 5 base 1 raised 4. So here product becomes a sum, same here, and division becomes difference, same here. And the next one is power rule. The x would come out and we would have x log base 2 8. When we use power rule, the entire term has to be inside the logarithm, so it is important that we pay attention to that. What I mean to say is log base 2 8 raised x is not the same as log base 2 8 raised to the power of x. So note the difference. What just happened? So I guess we'll just go back and write the stuff. So sum becomes difference. Sorry, our product becomes sum. Quotient becomes difference. And the same thing is happening over there. With power rule, it's better to put parentheses in the sense we have to keep in mind that log base 2 8 raised x is not the same as log base 2 8, the entire thing raised to the power of x. So we want to expand the expressions here. So this is a quotient, e raised 5 is divided by 11. So we can write it as ln e raised 5 minus ln of 11. And if we use the power rule, the 5 would come to the front. So 5 ln e minus ln of 11. And I mentioned in one of my previous videos that ln and e would sort of disappear when it's of that form. So we would reduce here to 5 minus ln of 11. Here we have a product. So log 100 plus log x, so product becomes sum, but log simply means base 10. So I'm just going to write the base and realize that 100 can be written as 10 squared. So if we move the 2 to the front, we have log base 10 of 10 plus log base 10 of x, and those two sort of disappear because of the properties of log, and the answer simply ends up being 2 plus log base 10 of x. Here we have ln of x raised 1 over 3. There is a power. The power moves to the front, and we have 1 over 3 ln of x. There is nothing we could do beyond that point, so we would just leave it as is. So here in part D we have product, we have power, got a whole bunch of things going on. So we start with the product. There are two terms, x raised 4 times the third root of y. So I write it as a sum. And the 4 can move to the front, so 4 log base b x. And I could rewrite the third root as y raised 1 over 3. So what we have is 4 log base b of x plus 1 over 3 log base b of y. Keep in mind, I cannot combine these two terms and write it as a product because of 4 and 1 over 3. We could only write the sum as a product if it is simply log base b of m plus log base b of n, in which case I could write it as a product. If there is any number in front of the logs, we can't do it, any number other than 1. So in this example, we have a whole bunch of things going on with log base a. So let us start with quotient rule. So in the numerator, we have that term. Denominator, we have the other term. So we can write it as x raised 4, third root of x plus 5, minus log of x plus 2. The entire thing is squared. That power can move to the front. So we have 2 log base a of x plus 2. In the first term, we have a product. So we could split it up and write it as log base a, x raised 4, plus log base a, the third root of x plus 5, which we can write it as log, the power would come to the front, 4 log base a of x, plus log base a. I could rewrite the third root of x plus 5 as x plus 5 raised 1 over 3, minus 2 times log base a of x plus 2, 4 log base a of x. The 1 over 3 is going to move to the front. We have 1 over 3 log base a of x plus 5 minus 2 log base a of x plus 2. In example 2, we want to condense the expressions. In other words, we have to combine. Keep in mind, we can only combine using the sum to product version of the log if those two numbers, 2 and 1/3, were not in the front. So we're just going to move it back them inside the log. So we have ln of x squared plus ln of x raised 5 raised 1 over 3, which would simply be ln of x squared plus ln of the third root of x plus 5. And now we simply have 1 here and 1 there, so we can combine the logarithms and write it as a product. So it would be ln x squared and the third root of x plus 5. The same argument goes with the next one. We have to get rid of that 4 for us to combine the logs. So I'm going to move it to the power. I could write it as log x minus 3 raised 4 minus log of x. Since there is a difference between the two logs, we can write that as log of x minus 3 raised to the power of 4 divided by x. In part C, a whole bunch of things are going on. So first step is to look at the first term. 2 is in front, which would prevent us from adding the natural logarithm, so we can write it as ln x plus 5 raised 2 minus ln of x minus ln of x squared minus 1. And we simply have ones here, 1 there, -1 and -1. But before we proceed, we can only combine two terms at a time. So I'm going to pull the negative out and write it as ln of x plus ln of x squared minus 1. And those two terms, since there is a plus sign in the middle, we could write it as ln of x times x squared minus 1. And now we have two natural logarithm terms. There is a minus term in the middle, so we could write it as ln of x plus 5 squared divided by x times x squared minus 1. In other words, that term divided by that term combined inside one logarithm, and we're dividing because there is a negative between the two natural logarithms. If there is a positive sign, we would be multiplying. So here is something called a change of base. So if we have log base b of x and log base divided by log base b a, then we could simply write it as ln of x divided by ln of a, or log base 10 x log base 10 of a, depending on the base. Now, if we go back in reverse, log base a of x can be written in terms of any base, which is b here, and it's simply log base bx log base b a. So the key thing to note is this part. And simply change this to any base, and I'm going to show you how this can be done in an easy way. So let's take the first expression, log base 8 of 32. I could write this as log base 8 of 8 times 4. You may say, well, why is he doing in terms of 8 times 4? Because the base is 8. So if I write it in terms of 8, then I can simplify. Inside the log, we have a product, so we can write it as log base 8 of 8 plus log base 8 of 4. And the first term would simply become 1. I'm running out of space here because those two sort of go away. 1 plus log base 8 of 4. And that is simply equal to 1 plus log base 10 of 4 over log base 10 of 8. It is the same as ln of 4 over ln of 8. So I see it as simply taking the log of 4 here, log of 8 there, and divide it. Or you can take the natural log. It's entirely up to you. So here we have log base 27 of 9. I could write 9 as 27 divided by 3. Again, why should I do it in terms of 27? I'm doing it so that I can simplify because of the fact the base is 27. So that would equal to log 27 of 27 minus log 27 of 3. So those two would simply go away and result in 1. So we have 1 minus log base 27 of 3, which I can write it as log of 3 over log of 27, and that is the same as saying ln of 3 over ln of 27. Those two are equivalent. They would give you the same answer when you plug it in the calculator. Use a different color and start from the top so that we have space. So I want to write this as log base 5, and I could write it as 2 raised 5. 32 is simply 2 raised 5, and if I move the 5 out, I'd have 5 log base 5 of 2. And here I'm taking a different approach because I cannot write 32 in terms of 5. So, which is why I'm writing it as 2 raised 5. So 5 times log of 2 over log of 5, and it is the same as 5 times ln of 2 over ln of 5. So log 0.8 of 16, I could write that in terms of base 0.8. If I multiply 0.8 by 20, I would get 16. So I'm rewriting 16 as 0.8 times 20. And you may ask me, why is he writing in terms of 0.8? I'm doing so because the base is 0.8. Now I could use product rule and separate it as ln 0.8 of 0.8 plus ln of 20. It's not ln, I meant to say log. Let me take that back. Meant to write log 0.8, rewriting 16 as 0.8 times 20, which would equal to log base 0.8 plus log base 0.8 of 20. Those two sort of go away, gives 1 plus log 20 over log 0.8, which is the same as 1 plus ln of 20 over ln of 0.8. We can take this one step further, but I'm running out of space, so we can rewrite this term because it is a log base 10, and 20 can be written in terms of 10, 0.8 can be written in terms of 10, and we can simplify it further. I'm going to leave that as an exercise. So, the first one we have to expand, so log base b, square root of x times y cubed minus log base b of z raised 3. There is a product in the first term, so I could write it as log base b square root of x plus log base b y cubed minus log base b z cubed. I can write square root of x as x raised 1 over 2 plus log base b y cubed plus log base b of z cubed. The powers come to the front, So we have 1 over 2 log base b of x plus 3 log base b of y plus 3 log base b of z. So here in part B we have to condense the expression, so we can only do that if those numbers 4, 7 and 3 weren't there. So what we're going to do is we're going to move it inside and type that x raised 4 plus ln y raised 7 plus ln x raised negative 3. And now we have everything with 1 in front, so all of those are in product. And here I can combine all three logs straight away, even though I mentioned earlier that you need to have two terms to combine, but with practice you can combine multiple logarithms right away, as long as the coefficient before the natural logarithm or logarithm is simply 1. So since all of them are in product, I could write it as ln x raised 4, y raised 7, x raised negative 3. I could write x raised negative 3 as 1 over x raised 3, and that term and that term could be simplified when combined, so we have ln x times y raised 7. So log base 16 or 57.2, we can evaluate it using a calculator if it is written in terms of base 10 log or natural logarithm, but we know using change of base formula that is equal to log 57.2 over log 16, and it is also equal to ln of 57.2 divided by ln of 16. So you could use the calculator to evaluate the log of 57.2 divided by the log of 16, or you could use natural logarithm and find ln of 57.2 and divide it by the ln of 16. So we move on to exponential and logarithmic equations. An exponential equation is one that has exponentials in it. A logarithmic equation is one that has logs in it. So when we have exponential functions, we have to ask the question if the bases match. In the sense, we have 2 raised x equal to 2 raised 22 minus x. The bases match. If the bases match, we simply set those equal to 0 and we solve. If not, we take the log, isolate the x, then we solve. I simply say if you have an exponential equation, you take log on both sides. If you have a logarithmic equation, you take exponentials on both sides, provided, as shown in this example, you should have one exponential on the left, one exponential on the right, or a simple term. So I have 5 raised 3x minus 6, and I can directly equate these two if I rewrite 125 as 5 raised 3. Since the bases match here, 5 matches with 5, we can directly equate them and write it as 3x minus 6 equal to 3, which would mean 3x is equal to 9, which would imply x is equal to 9 over 3. So the solution is simply 3. Here, look at that base, that is 2 and that is 4. The bases do not match. So could we write it in terms of a base that could match? So 8 and 4, both of them have a common factor of 2. So we have 8 raised x plus 2 equals 4 raised x minus 3. how could we write 8 in terms of 2? I could write it as 2 raised 3, which is 8, raised x plus 2, which would equal to 2 raised 2 raised x minus 3. Using the properties of exponents, we could multiply those two terms and those two terms. So we have 2 raised 3 times x plus 2 equals 2 raised 2 times x minus 3. The bases match now, so we could write it as 3 times x plus 2 equals 2 times x minus 3. If we distribute and solve, we have 3x plus 6 equals 2x minus 6. Move all the x's to one side, numbers to the other. 3x minus 2x would equal negative 6, negative 6, which would imply x is negative 12. Now here is an example in part C where no simplification is going to do a great deal for us, because we have an base 8 exponential, and there we have 1 over square root of 2. But if you realize, we could write 8 as 2 raised 3 raised to the power x. And 1 over root 2 can be written as 1 over 2 raised 1/2. So seems like 2, the base 2 is coming into picture slowly. So 2 times 3x. We can multiply those two. Would equal to, we move the denominator to the numerator, so we have 2 raised negative 1/2. The bases are identical, so we simply equate the powers. Now we divide by 3. The answer is negative 1 over 6. So here in example 2, we have entirely different bases. So since the bases are completely different, the only way to solve this is by taking logarithms on both sides. So let's take, you can either do base 10 or you could do base e, entirely up to you. I'm going to do base e. So 3 raised to x minus 1 equals ln of 7 raised x plus 1. So that term and that term are in the power, so we can move that to the front. 2x minus 1 times ln of 3 equals x plus 1 times ln of 7. Distribute and multiply 2x times ln 3 minus ln of 3 equals x times ln of 7 plus ln of 7. These two are simply numbers, and the others have an expression, so we move all the x's to one side, numbers to the other. 2x ln 3 minus x ln 7 would simply equal to ln of 7 plus ln of 3. And x is in common in the left hand side, so if I pull that out, I have 2 ln of 3 minus ln of 7. Since there is a plus here, and we have ln of 7 plus ln of 3, I could write it as ln of 7 times 3, which is 21. On the left-hand side, I can't combine the logarithms yet. because there is a 2 in the front. So I'm going to move the 2 back into the power. That becomes ln of 3 squared, and 3 squared is 9, minus ln of 7, and that would equal to ln of 21. We could write ln of 9 minus 7 as ln of 9 over 7. That would equal to ln of 21. So the answer is ln of 21 divided by ln of 9 over 7. So in this problem, before we proceed, we have to do some simplification. Move all the numbers to one side, x's to the other. So 7 e raised to x would equal 58 plus 5. So that would be 63 equals 7 times e raised to x. Divide by 7 on both sides. E raised to x would simply equal to 63 over 7. 63 over 7 is 9. And there is no way, well, there is a way in which I could write 9 in terms of e, but it's going to have decimals. So I'm simply going to take natural logarithm on both sides. So ln of e raised to x would equal ln of 9. We could move that power to the front. 2x times ln of e would equal ln of 9. ln and e sort of go away and become 1. So we would have 2x equals ln of 9, which would mean x is equal to ln of 9 over 2. Part C looks like a problem that we just couldn't solve because there is no way we could isolate only exponentials in raised to the power of some x and the numbers to the other side. It is just not possible no matter how hard you try. But in a problem like this, you should realize that I could do something called substitution. If I set u equals e raised x, I could write e raised to x as e raised x raised to the power 2 minus 8 e raised x plus 7. But I made a substitution that u is equal to e raised x. So I can rewrite this equation as u squared minus 8u plus 7 equals 0. Which, if you observe, is a quadratic equation. And we can solve a quadratic equation either by using factoring or the quadratic formula. This particular equation is straightforward because we can factor it as u minus 1 times u minus 7 equals 0. Therefore, the solutions are u equals 1 and u equals 7. But we are not done yet. We found the solution for u, but the question wants to find the solution for x. So let's go back to our initial substitution. Recall, u is equal to e raised x. Therefore, when u is equal to 1, 1 would equal e raised x. Take ln on both sides. ln of 1 would equal ln e raised x. ln of 1 is 0. And bring the x to the front, we have ln e. Those two sort of go away and become 1. So x is 0. That is the first solution for x. Now, when x is equal to 7, when u is equal to 7, we have 7 equals e raised x because our substitution is u equal to e raised x. So 7 would equal to e raised x. We take the natural logarithm on both sides. Ln of 7 would equal to ln e raised x. Move the x to the front. We have ln of e times x. That would equal to ln of 7. Those two sort of go away and become 1. So x times 1 is x equals ln of 7. Therefore, the second solution of x is ln of 7. So I'm going to write an important remark. Note, when you make a substitution, make sure to undo the substitution to find the solution. The undoing part is right here. We kind of go back to our substitution, plug in the value of u, and solve for x.